So thank you for the introduction. So yes, I'm a PhD student. My name is Marouane Il Idrissi, and I work at EDF Research and Development. EDF is the France's main electricity producer, and as well as in l'Institut de Mathématiques de Toulouse. And I'm supervised by four persons, so Nicolas Bousquet, Fabrice Gamboa, Bertrand Yos, and Jean-Michel Loubès. And the main bulk of my work is actually working on the mathematical foundations of interpretability models of interpretability methods for better understanding black box models. And so I'm going to share some results, some interesting things. I hope that I'm going to convince you that it's interesting about cooperative game theory and the trying to quantify importance. So for context, we have a fairly simple question, which is that given some random inputs, x1 to xd, and some random output, which is just a function g, which is we're going to assume to be black box, how much does each input contribute to the variance of the random output? So basically, this is what importance quantification is. And here G is considered to be a deterministic black box model. So it means that it can be a numerical model. For instance, in the field of sensitivity analysis, it's fairly used. It's a simulation codes in order to simulate the behavior of some like physical phenomenon, or it can be a machine learning or deep learning model. So this is what we do in post hoc interpretations, basically. And the little twist in my studies is that I generally do not assume that my inputs are mutually independent. So that raises a lot of questions. So there have been many methods that have been proposed, and one of which was proposed by Artwen in 2014. He took an inspiration from cooperative game theory and in particular the Shapley values in order to answer this question. So in this talk, we're gonna dive into how cooperative game theory can be useful for this problem and what the Shapley values are. And we're gonna try to draw a link between cooperative game theory and some results from the field of combinatorics. And then we're going to open on some interpretation challenges. So yeah, cooperative game theory, in a nutshell, you can understand it as just the art of cutting a cake. So formally, I have two things. The first thing is a set of player, which is I'm going to denote D, and a subsequent set of coalitions of players. So P of D is the power set of D. It's all the set of subsets of D. Okay. Then I have a value function, which is a set function, which takes a coalition of players and outputs a value in R. And its goal is to quantify the value produced by a coalition. And the coupled DV, it defines what's known as a cooperative game. And the main question is how can we redistribute V of D, V of D is going to be the cake, among each of the players that in D. And the answer is by using allocation. So what's an allocation? An allocation can be understood as a description of the cake cutting process. So basically we have players, we have different values for every coalition of players, and then we're going to aggregate those values in some way in order to build allocations. But we can do this in many different ways, but there are two criteria that are going to be of interest. The first one is efficiency, which only states that the sum of the values of the allocation must be equal to the whole cake, to V of D. And the second one is non-negativity, which means that each of the value is greater or equal to 0. This helps ensure that we actually allocate the whole cake and nothing but the cake. So there's an interesting construct in cooperative game theory, which are known as the Harsanyi dividends. And the Harsanyi dividends of a cooperative game, so I'm not going to go into the details. The main thing that you need to keep in mind is that the Harsanyi dividends are in blue here. They're just like some weird sum of the -1, which is still always going to be in green, times the value, the value for a coalition. And they can be interpreted as the surplus due to a coalition of players, the added value due to a coalition of players. And there's an interesting property is that if I were to sum over every coalition to sum those dividends over every coalition, I get back the whole cake. And they can be interpreted as on the left, the diagram on the left. So the diagram is the whole cake. And then I'm going to have values for every possible coalition of players. So there's a typo here. I'm sorry, it's supposed to say 2, 3. So yeah, now, Shapley values. The Shapley values, they're nothing more than just an egalitarian redistribution of the Harsanyi dividends. I take the Harsanyi dividends, and then I'm going to divide them. I'm going to divide it in two. For example, the Harsanyi dividend that is due to the first player and the second player, I'm going to divide it in exactly in two. I give half to the first player and 2 to the second player. The Harsanyi dividend due to three players, this is going to be the same thing, but I'm just going to divide it for 3. And they can actually be interpreted as an a priori assessment of the situation based either on either ignorance or disregard of the social organization of the players. We can understand the Shapley values as being like, it's kind of like a uniform prior on the underlying redistribution process that goes on in the cooperative game. So we can generalize this idea. So this is not something that we've invented. It's from cooperative game theory, and it's the Harsanyi set. The Harsanyi set is a set of allocations that can be written like that. So instead of dividing dividend over the cardinality of the set A, we can just reweight them by some lambda A of I under some constraints. But what's interesting about every allocation that are in the Harsanyi set is that they are always efficient. So it means that we are always going to be allocating the whole cake. And if V, the value function, is monotonic, then they're always going to be non-negative. And by monotonicity, what I mean is that a bigger coalition must have a greater value than a smaller coalition. If B is included in A, or 2 coalitions, the value of B must be less or equal than the value of A. So now for importance quantification, in the field of sensitivity analysis, by analogy between players and the inputs of a black box model, Arthouen proposed to study a very particular cooperative game where he chose the value function as being this ST, so in the literature it's known as the total Sobol indices, which is just an expectation of a conditional variance. And the idea being that if I were to forget the normalizing constant by the variance of g of x, st of d, so my cake, is going to be the variance of g of x. That's the whole idea. Basically, by choosing this value function, my cake becomes the variance of g of x. And the Shapley effects are actually the Shapley values of this particular game. And the thing is that this value function is monotonic, so the Shapley effects are always efficient and non-negative. It means that they can be interpreted as shares of variance allocated to each input, which answers the initial question. However, the first thing that we encountered is that there's a drawback. And this drawback is that those effects, those indices, do not detect exogenous inputs. And by exogenous, I mean an input that is not in the model. So for instance, for this little experiment, if I were to have g of x being equal to x1 plus x2, but I would consider 3 inputs with an additional one, x3, which is exogenous, it's not in the model, where x3 is correlated with x1, so all of them follows a multivariate normal distribution, then we can see that if rho is different than 0, the Shapley value, the Shapley effect allocated to x3 is actually strictly greater than 0. And this can be a problem if you want to spot exogenous inputs in correlated setting. So what we did is that we took an inspiration from the Harsanyi set and we chose to study another value, not the Shapley value. And this value is the proportional value. And it was introduced by Hartmann in the 2000s. And the overall idea is that the redistribution of the Harsanyi dividends are not equal, but they are going to be proportional. That's the gist of it. I'm not going to go into deep into the theory behind how they work. And they can be interpreted as that each player gains in equal proportion to that which could be obtained by each alone. A bit convoluted, but that's the main idea. So when we apply those proportional values, so there's a bit of work in order to apply them, it resulted in what we call the proportional marginal effect. So it was introduced by Margot Héran. It was the work of her internship. She was my intern for a while. And what we saw is that those effects, those indices, do tend to discriminate more than the Shapley effects in highly correlated situations. And there's a nifty little proposition that says that under, so if we suppose that we cannot express the inputs as functions of each other, so it's like multicollinearity, but non-linear, okay, they cannot be functions of each other, then a PME equal to 0 is equivalent to a variable being exogenous. So we solve the problem of detecting exogenous input. So now I'm going to go really quick on the estimation, but the idea is the main thing is that it takes a long time. We need to estimate the value function for every possible coalition. So there's 2 to the power of d of them. This is a problem that grows with exponentially with the number of inputs. And there are basically 2 ways to do it. The first one is using Monte Carlo sampling, and it requires the ability to being able to sample from the inputs distribution and every possible conditional distribution of the inputs. And it's proportional to d factorial model evaluations, which in machine learning, this is not a problem, but in instances of numerical model that can take up to a month in order to have one evaluation, it can be a problem. But there's also another way to do it. It's given data, where we can actually estimate those quantities using a nearest neighbor scheme. And in this case, we only need to observe an IID input-output sample. But it still requires 2 to the power of d estimates. Yeah. So for an illustration, so we're going to take a bit of a somewhat realistic use case, which is an optical filter. So in this case, the optical filter is it is comprised of 13 different layers, and each of these layers, like you have to think about it, like this filter, what it does is that whenever there's light coming through it, the light scatters into the filter, then regroups and comes out at the end. And my inputs, my variables, are gonna be the refractive index error of each of the filter. So the filter are not perfect, so they do have an error. And these errors are going to be highly correlated due to the manufacturing process. So we've put, so they're uniformly distributed, and we've put a Gaussian copula with the rho equal to 0.95. And the black box model, what it does, it computes the transmittance error with respect to the perfect filter, the one which for which the layers do not have any error, basically. So in this case, we only have access to an IID input-output sample, and we use that data-driven approach in order to compute the indices, which look like that. So on the left, you have the Shapley effects, and on the right, you have the proportional marginal effects. So the first thing we can see is that there's no exogenous input, which is nice. But the second thing that we can see is that the Shapley effects tend to squish the importance, like every input is somewhat on the same range between 5% and 10%, whereas for the proportional marginal effects, we're varying between 2% and 21.5% of the output variance. So what we can do now is to perform feature selection based on this importance ordering. So what we want to do is to build a surrogate model, which is going to be a Gaussian process of this numerical model, because, for instance, it takes a long time to evaluate. So if we use the whole data set, we have a Q squared. So Q squared is the R squared computed on a leave one out scheme, equal to approximately 99.5%, which is really good. And then if we were to put a first threshold of 2.5% importance, stating that every input that has less than 2.5% importance, then I'm going to remove them from the model. For the Shapley effects, no features are removed because like everybody seem to be important according to the Shapley redistribution. But for the PME, we have two inputs that are removed, resulting in a Q squared of still really good, 99.14%. And we can do the same thing with 5% importance. And for the Shapley effects, no features are still removed, but for the PME, we can remove 7 inputs and we still have a really nice Q squared. So now, for the links with combinatorics. Let's just recall what we did. The first thing that we did is that we chose a value function, v, a set function, and then we defined Harsanyi dividends this way. Well, the thing is, something that we found is that it's intimately linked to a well-known equivalence in the field of combinatorics, which is known as a generalization of the Mobius inversion formula on power set. And this result states that for any two set functions which are valued in an abelian group, so abelian group means like I just need to define how to add stuff together, not even multiply stuff together. We can think about matrices, for instance. Then we have the following equivalence. And what I want to draw your attention to is the left-hand side, which looks exactly it looks exactly like what we did with the Harsanyi dividends. And from the right-hand side, we went to the left-hand side in order to interpret them. So here, this is what I said when I said that the sum of the Harsanyi dividends were equal to the cake, basically. And this is what we call the input-centric approach, okay, going from the right-hand side to the left-hand side. But there are some problems with doing that, in the sense that one of the main issue in importance quantification, especially whenever the inputs are dependent, is to being able to quantify what is due to by interaction, meaning functionally speaking by the model, and what is due to the correlation, the stochastic nature between the inputs. And if we were to compute, so for still a simple model, which is equal to x1 plus x2 times x3, we can see that in the independent case, whenever I choose my value function to be equal to the total Sobol indices, the same as before, my Harsanyi dividends grants half of the output variance to the first variable, which makes sense, and half of the variance to the interaction between x2 and x3, which also makes sense. But as soon as rho is different than 0, we can see that we have some other terms due to the correlation, which informs us basically that using this value function taints, in a sense, the quantification by mixing somehow the correlation with the interaction. Ideally, it wouldn't have to change. Basically, we would have the same thing whether they are independent or correlated. And in both cases, the sum of those dividends are equal to the variance of g of x. So the precise interpretation of those quantities, the dividends, is still an open question. They're a mixture of interaction and dependence effects, but the question is which mixture? And we don't know, we don't have an answer to that. And then we can recall that the Shapley effects are just the linear aggregation of those dividends, so we can understand them as being an egalitarian aggregation of a not so clear mixture of interaction and dependence effects, which hurts a bit even though the output is nice, which means that it can be interpretable, we cannot like really understand what it quantifies. So in essence, choosing this value function leads to an uncharacterized quantification when the inputs are dependent. So, in conclusion, a few key messages. First, cooperative game theory is really resourceful for building interpretable importance indices. It's been used in explainable AI also a lot with SHAP. The Arseny dividends are really nice in the sense that it can link the field of combinatorics through the notion of a Mobius inversion. The Shapley values, they're an egalitarian redistribution, which is not the same thing as being fair. The proportional marginal effects, they allow to detect exogenous inputs and is a bit more discriminative, and the estimation is very time consuming, but this is a problem that is embarrassingly parallel as well. And some challenges and open question. First, is it possible to drive the estimation cost down? And the answer is in specific cases for a linear G, for instance, it's possible using a PCA. And for the interpretation problem, we would have to go to do a model-centric approach, which is instead of going from a right-hand side of the equivalence to the left-hand side, do it the other way around. It amounts to doing a functional ANOVA with dependent inputs. And we've worked a lot on this, and we have a lot of interesting things to say about it also. And there are many others allocation in the literature, which can be interesting to study the properties. So here are some references. We have two preprints if you want to go, one on the PME and the other on the links with combinatorics if you're interested. And I thank you for your attention. And if you have any question, I would be glad and to try to answer them. Thank you.
Yeah, many thanks, Marouane, for the very interesting talk. So any questions for our speakers? Maybe let me try to ask one question.
Yeah.
Actually, not very familiar with these Shapley values, but I think your talk is based on game series, which has some connections to like multi-agent reinforcement learning. So in reinforcement learning, we also have like the notion of the value function. So could you maybe briefly discuss like, is there any connections between multi-agent reinforcement learning and your work?
So if I'm not mistaken, in reinforcement learning, it deals more with non-cooperative game theory, where basically you have two agents that need to compete with each other, which is procedural in a sense. You can see it as a chess match, for instance. What is the best step, the best best way I can play this the game at one point. Whereas for cooperative game theory, this is not actually the same thing. This is really trying to allocate resources from this is really to trying to cut a cake, basically allocate resources to players based on the way that they interact with each other through the value function. So, but maybe there's some cooperative game theory in reinforcement learning, but I'm not really aware of it.
Thank you. Yeah, in reinforcement learning, we also have like competitive reinforcement learning, as you have mentioned, like two players compete against each other. And we also have like a collaborative multi-agent reinforcement learning where like multiple agents collaborate together to complete some tasks.
Yeah, but the thing is that the thing is that cooperative game theory, like this is, I think it's like on the first paragraph of the first chapter of every cooperative game theory book, which states that the name cooperative is not well chosen because it doesn't mean that there needs to be a cooperation. Like for instance, if you take the proportional values, so there's no cooperation here. Like the one that brings the most value takes the most. So they're not cooperating in a sense. So it's more of a division kind of way to think about it.
It's really about allocation.
Yeah, essentially. So yeah, and you can be cooperative in non-cooperative game theory, and you can be non-cooperative in cooperative game theory. So this is like the notion of cooperativeness is not linked to the name, basically.